And we can kind of see this in example in action here, where we go a little bit further, and this is what we call, and we've seen this in previous video casts, but what you can see here is if we look at the panel on the left, you can see the velocity against force. Now this is really important because this connects to a lot of what we have seen previously in terms of our physiology. If you go back to video cast 1, which is high intensity physiology, where we're talking about energy systems, for example. So just look at the solid line. The solid line represents the association between force and velocity. So what you can see is that when the amount of force which is on the y-axis, that is the horizontal axis, when we're trying to produce the highest amount of force, that occurs at the slowest velocity. You cannot move a heavy load fast. You can try to move it fast, but you cannot move it fast. Whereas what you see is when the relative velocity, when the relative force or the power that's being produced is low, force that in this case is low, let's say at 20 in terms of whatever these units are, the velocity is much higher. You can move it far, far more quickly. Well, why is that the case? Well, it's absolutely fundamentally to do with the amount of muscle fibers that we need to recruit. In order to be able to generate that force, you have to recruit more fibers. More fibers are needed, therefore the amount of time it's going to take to generate that force is going to be slower. Now what you can also see on that graph then is the interaction between the force and velocity and power. So power is the dashed line, and what you can see is that the power is not occurring at the highest velocity. Okay, it's not occurring at the highest velocity. What is actually happening is that the power is a function of the amount of force being produced and the amount and the rate at which that force is being produced. And not surprisingly, if the velocity of shortening is slow, and remember that power is how quickly you move the object, if the velocity of shortening is slow, then the power has to be low. If the velocity of shortening is really high, then the amount of force we are producing is low. So power sits very much in the middle of that kind of relationship. And then what you can see on the right-hand panel is just the difference between different muscle types. So you can see it for a long, thin muscle, and you can see it for kind of what is referred to as a short, fat muscle. And so you can see that our relationships change depending upon the muscle fiber that we are, or the muscle structure that we are looking at. That force velocity is really important, because once we understand this, what you are starting to see is the basic principles of muscle physiology. That the muscle physiology is absolutely governed by this, but so too is our understanding if you think about substrate metabolism. Substrate metabolism follows that same relative association between force and velocity. Remember that what we talked about was if I want to produce a really high velocity, really high power output, I'm going to have to probably use ATP-PC, but I can only maintain it for a short period of time. If I want to produce a sustained amount of force, I'm probably going to be able to use aerobic metabolism, but it's going to come at a much, much lower amount of force being generated. I can maintain it for a longer period of time. So the same relationship exists both in terms of substrate metabolism of what you see here in terms of muscle mechanics as well. And here we can see it in real action. So this is some data that was published back in the 1970s, but it's a really nice data set. And what you can see is, if you look at the panel on the left, what you've got is a series of muscle actions, and what they've measured is the amount of force being produced for each of those given actions. So whereas what we'd seen on the previous examples were kind of just schematics, this is real data. And so what you can see is when the amount of force being produced is at its highest, the velocity of shortening is at its slowest. So what you should be able to ascertain here is if there is zero velocity, think about what muscle action that would be. So the zero velocity, is it lengthening or shortening? Well, if the zero velocity is neither lengthening or shortening, therefore that must by definition be isometric. So you've got an isometric contraction sitting at the top, and then we start to move into these other contraction types, which are actually, in this example here, these are concentric, and I'll explain why they're concentric later in this session. But as you can see, as the load, as the velocity of shortening increases, the amount of force being produced starts to decrease. And you get this lovely relationship that you can see here, this kind of exponential relationship that we see here, till the point where you in essence get a really high velocity of shortening, but it's occurring with almost no resistance being applied. On the panel on the right, what you can see then is the power that is associated with those. And don't necessarily worry about the data from Hill, which is total energy liberation, but just look at the mechanical power output. It is exactly as we saw in the previous schematic, that the highest power output is actually occurring, at this case, at probably around about a velocity of about 0.4, and it's occurring really in terms of about 0.1 in terms of the amount of force being produced. So it's not occurring at the highest velocity. It's not occurring at the highest amount the lowest velocity or the highest velocity. It's occurring kind of in that in-between point. So you're seeing the force-velocity relationship in action. And of course that then links to fibre types. So we clearly know that a fast-twitch fibre is able to produce more force. So if we're thinking about high forces are going to be produced predominantly through fast-twitch fibres. Now fast-twitch fibres have very fast twitch responses, but are highly fatigable, as we saw early on. Whereas a slow-twitch fibre produces far less force, but it has far greater fatigue resistance. So fundamentally, what you have seen in the course of this first part of this session are very much the kind of the ways in which the structures and functions of our muscle fibres interact to being able to generate force.